When molecules in a sample of matter have no attraction or almost no attraction to each other, they will fly any which way. That sample of matter will be a gas. When the attractive forces between molecules are sufficiently strong, the molecules stick to each other. The attraction causes a substance to be a liquid. We have talked about properties of gases before. Now let's go over properties of liquids. Liquids have no definite shape. They assume the shape of the container they occupy. Unlike gases, the liquids take the lower part of the container, not the entire space. Liquids are incompressible. We cannot force them to occupy smaller space as we did with gases. The reason for it, the absence of space between the molecules. Molecules in a liquid are shoulder to shoulder, so to speak. Also, we remember how the increase in temperature led to considerable increase in volume of gases. Liquids also increase in volume when temperature is rising, but it's only very small increase. Liquids can flow. This property liquids share with gases. Liquids also have viscosity, a resistance to flow. When we spill liquid water, it doesn't travel everywhere. The pool of spilled water is in one place. As the spilled water flows on the surface of a table, the molecules in it tag on each other, keeping our pool of water in one location. Liquids can evaporate and they have surface tension. The tension of the surface layer of molecules in a liquid caused by the attraction of the particles in that surface layer. Evaporation is the process in which molecules from the surface of a liquid gain kinetic energy to overcome surface tension and escape liquid. You might have noticed that if you leave a glass of water standing for a while, the level of water in the glass will decrease. What is happening? Molecules inside of the liquid are not still. They have kinetic energy. They are moving and bumping into each other and passing some of that energy to the surrounding molecules. Some molecules in the surface layer might gain enough kinetic energy to overcome attraction of the molecules in the liquid and go flying. As you know by now, the average amount of kinetic energy represented by temperature. So the higher is the temperature, the more kinetic energy is there in the particles of our liquid. Evaporation can occur at any temperature, but its rate tends to increase with temperature. The higher is the temperature of the more molecules will be able to have enough kinetic energy to break away from the surface of the liquid. The temperature of the remaining liquid drops during evaporation. Let's discuss why. This phenomenon is called evaporative cooling. Let's think about it this way. Our school has a track team, so we have runners. And let's say the coach decides to keep track of how well team is doing by averaging the speed of our runners. So now let's imagine that some other school came to us and they invited our best runners to go to a different school now to be trained for Olympic team or something like that. Okay, so our best runners decided to leave and go training with that school. What do you think will happen to the average speed of our team? Our fastest runners are gone, and as a result, average speed of the entire team will drop significantly. The same happens to the liquid water after some molecules evaporate. It is the fastest molecules with the highest amount of kinetic energy that were able to overcome the attraction of the surface of the other molecules. They left. We still have considerable amount of molecules, but on average they have less of the kinetic energy in them and the temperature of the liquid left behind is lower. Molecules that vaporized and went flying are now a gas, or more specifically, they are vapor, a gaseous form of the liquid that stays at the bottom of the container. Since vapor is a gas, it can exert pressure, all that flying around and colliding with the walls of the container that will exert pressure, vapor pressure. The amount of vapor pressure depends on two factors: intermolecular attraction between the molecules in a liquid and temperature. Let's say we have two flasks with the same compound in it, same liquid. And one liquid is at the temperature 20 degrees Celsius and another at 75 degrees Celsius. Well, I will draw some molecules for both liquids. I only drawing surface molecules because it will take too long to draw all of them. Okay, so at temperature 20 degrees Celsius, some molecules would be getting enough energy and escaping the surface of the liquid, and they will go flying. The same process will be happening in the other flask at 75 degrees Celsius. Some molecules would be escaping the surface, but since the temperature in the flask on the left is higher, it means that this entire liquid contains higher amount of kinetic energy. So at the end of the day, more molecules at the surface will be able to escape the attraction of the liquid and go flying. As a result, more molecules will be up in the air, flying, colliding with the walls of the container, producing pressure. More collisions, more pressure. So the higher temperature leads to higher vapor pressure. This time I have two flasks with different liquids, both of them at the same temperature, 25 degrees Celsius. So the temperature will not be playing an important role in affecting vapor pressure in this case. But my liquid on the left has weak intermolecular forces. It means that those molecules inside of the liquid phase of this substance, they are attracting to each other, but not as strongly. Their intermolecular attraction is relatively weak, while substance on the right has a strong intermolecular attractions. Those molecules in the liquid, they are attracted very strongly to each other, meaning they are holding on each other, taking each other pretty strongly, preventing molecules from escaping. The amount of kinetic energy in both substances is the same. So in my substance on the left, because of the weak attractive forces between molecules in a liquid, considerable amount of molecules will be able to escape, and they will be flying up in the air, producing the vapor pressure. In my substance on the right, some molecules still will be able to escape the tension, the attraction of the molecules in the liquid, but there will be fewer number of them that have enough energy for it, even at 25 degrees Celsius. So as a result, we will have less molecules flying above this liquid, and vapor pressure of this liquid that created inside of this flask will be lower due to the fact that molecules in the liquid are not allowing that many molecules to escape, vaporize from the surface. So we can say that the higher temperature leads to higher vapor pressure, and the stronger intermolecular attraction between the molecules in the liquid leads to a low vapor pressure above that substance. And vice versa. Lower temperature produces a lower amount of vapor pressure because less molecules would be up in the air flying and producing that vapor pressure, and weaker intermolecular forces of attraction between the molecules in the liquid would lead to many molecules being able to escape the surface and produce a lot of vapor pressure. Table H in the set of reference tables shows the change in vapor pressure of four substances as the temperature is increasing. You can see that all substances show increase in vapor pressure as the temperature goes up. No surprises here. Yet, on top of that observation, we can say that these four substances vary in the amount of vapor pressure they produce. propanol has higher amount of vapor pressure than ethanol, water, or ethanoic acid at any temperature. So we can deduce that the higher vapor pressure is the result of the relatively weak intermolecular forces between the propanol molecules in a liquid propanol. Because the forces of attraction are weak, many molecules manage to evaporate from the liquid propanol and participate in the creating of vapor pressure. Following the same logic, we can say that ethanoic acid has the strongest intermolecular attractive forces between its molecules compared to other three substances on this graph. Ethanoic acid has the lowest vapor pressure at any temperature, which means that its molecules in the liquid are holding on each other pretty strongly, preventing evaporation. Some molecules will still be able to evaporate, but not as many in propanol, ethanol, or water. The lower the number of molecules in vapor will produce the lower value of vapor pressure.